So today we are going to solve the problem increasing subsequence 2. In this problem, given an array of n integers, your task is to calculate the number of increasing subsequence it contains. If two subsequences have same value but in different position in the array, they are counted separately. Okay, so let's start this. Let's solve this problem. So previously we have solved the problem increasing subsequence. Okay, largest increasing subsequence. In that, what we have to do, we were given a subsequence. Let's say this is the array we are given. So we want to find out the largest subsequence. That was the previous question. But now what we have to do, we have to find out all the subsequence. Okay. So previously what we were doing, we don't want all the subsequence. We just wanted the length of largest subsequence. So we don't, in previous question, we didn't have any requirement of storing all the subsequence. But here we have to count all the subsequence. So we have to consider every subsequence. Okay, so that's why the previous method would not work here. Okay, so how we would do it? Okay. So the what if how we were finding the previous how we were finding the largest subsequence, or let's say how we can find a largest subarray means suppose if this was the subsequence. Okay, so now let's consider only subsequence ending at 4. Okay, if let's say that is TP of 4. Okay, so if we want the sum of all the index, so let's say this is the array and we have to find all the subsequence. Okay, so if we see individually, okay, so what can let's name this TP of I. What it will store? It will store all the subsequence ending at I. Okay, so in if we know the answer for this, let's calculate what are all the subsequence ending at this. So it would be just 1 because only we can start only this index. Okay, so 1. Now what are the subsequence ending at this? So now its count would be 2. How? So first is this, if we take only this element. Now we can, for a subsequence, we can take previous values which are smaller than this. Okay. So all the subsequence which are ending at 2 will also end at 3 if we decide to take this element. Okay. So that's why this is 2. So what is TP of I? TP of I is 1, the element itself, plus summation of all the TP of I j from 0 to less than I, means which are previously calculated. We want the sum of all the elements. Okay, summation of all the elements where j is greater than equal to 0, j is less than I, and the value at j should be less than value at I, because we want increase in subsequence. So only elements which are smaller than this element, we would take that only. Okay, so 2 is smaller than 3, so we have counted that. Now for 5, what would be the case? That would be 1. We can include this element. Now what if we decide to end here also? So every index that are ending at 3 will also end at 5, so plus 2. Now if we skip this element, we directly take from 2, so that would be plus 1. You can also prove like what would be this 4 index. First one would be the element itself, 5. The second was from ending at 2. So what were ending at 2? That was 3 and 5 and 2, 3, 5. And ending at 3. These both are ending at 3. These are ending at 5. And now what ending at 2? So that would be 2 and 5. So you can see that these are the 4 subsequence we get. Okay. So now for one it would be only 1 because there are no elements less than 1 previously. Okay. Now for 4 we can add this. So if 1 we can add 4 plus if we take 1 then it would be 1. Now we can't take 5 but we can take 3 and we can take 2 also. Okay. So this would be number here. Similarly for all the cases. And at last what we will do? What would be our answer? Answer would be summation of all the dp from I equal to 0 to n minus 1. Means summation of every subsequence ending at 2, ending at 3, ending at 5, similar, and so on. Okay. So now we know that if the complexity allowed was n square, then this is how we would have solved it. Okay. Because what we are doing for every index, I, what we are doing, we are checking j greater than equal to 0 and j less than I. What if v of value at j is smaller than value of I? Then simply we are adding that to our answer. Okay. So this is what we are doing. But as you can see, it has a complexity of n square. Okay, so what else we can do? I hope you get this part. Okay, so this is the basic part which you are doing till now. We applied it many times. Like if we want to something to end here. Okay, so we calculate this index. Now we check that what if it ended. What if we can add it to any another subarrays. Okay, so we are checking for every I. Okay, so now this would fail. Okay, so now what can we do? Eventually, what we want if we sort this array. Okay, now instead of looking at with index, let's look at number like ending at 0 plus ending at 1 plus ending at 2 and so on. What we are doing now? This ending at 0 is not index 0. Okay, this is actually value 0. So now if I rewrite the index 2, 3, 5, okay, it's something like this. So now this answer would not be added to dp of I. Okay, it would be added to dp of 2. That is what are elements ending at 2. This would be added to what are ending at 3. So now for any value, what we can do? We can add its value from all the previous value which are smaller than this. Okay, so all values which are smaller than this number. Okay, so now what we have simplified. Now what can we say? Now from this we can say that whenever we are calculating for 4, then instead of iterating through whole index n, means instead of iterating through whole array, what we can iterate, we can just iterate to value smaller than this. So what we can do, we can see how many. Uh, so in this example, now if we are here, then instead of checking these 4 values, what we will do, we will just check for dp of 1, dp of 2. We will simply directly add all the dp's smaller than this. So now it's kind of increasing. Okay. So every time what we are adding now. Okay. So if the current value is 4, then simply these 3 would be added here. Okay. If the current value is 5, then this 4 would be added here. Okay. If the current value is 3, then this 2 would be added here. Okay, so now we are only dealing with the previous values. Okay, but still, now also if the suppose the number was 10 to the power 4, then we would require to iterate through every possible previous index. Okay, so now what can we do? So now what if so here comes another data structure in the picture, that is segment tree. Okay, so I would highly encourage you guys, if you don't know what is segment tree, then you first learn what is segment tree, then come to this video. Okay, so basically what this you can search in net also. What is segment tree? You can find it good articles in CPLGO site also, and even you can see there are many tutorials online for this. Okay, so first understand what is segment tree, and then you can come back here. Okay, so now what we first simplified, we simplified that now we would only require the range update only. Okay, so what we did, we only now how we now we don't want now we only want the addition of every. So uh, I hope you guys understood. Let me show you. So what was the first issue? Issue was we were iterating for every we were iterating for every j index. Okay, so first we were storing jth value in DP, but how that was not useful because we are iterating through every n also. And the second thing was if we see it in if we see it as a segment, then let's suppose this was the question. Okay, so if we were to find this, first of all we were iterating through every index. Okay, and second thing that it was not continuous. Not continuous by, means if we have to for every index we have to see, okay, this we can take, so okay, this is a value, but this we can't take, so we have to skip this, and this is value. So if we see segment wise, okay, so we have to add two different segments from here. So one segment would be 0 to 1, and one would be 3 to 3. Okay, so why we are I will first, if you will understand segment, then you will see why this was creating an issue. Okay, although we have not improved the time complexity. Okay, now if we store the DP by its value instead of index, then we are not improving on time complexity. But what we have improved now for 4, we want whatever we want would be in one segment only. Okay, so if we have a method which would tell us that this is the sum of all the values between these. Let's say we have LNR and we want the sum between all LNR. So what we want? We want dp of L and so on till dp of R. Now let's say we have a method which gives us this. Okay, let's say we have a method. So in that case also, if we go by this method, then it would had me calculate 3 comma 3. Now again I am calculating this. So I was iterating n times because the segments were changing. Now by converting this to a single value, what we are doing now, everything is behind 4 only. So I can simply find out with a single query. L would be 1 and R would be 3. Now if I do a single query 1 and 3, then what I will get the answer? I will get the answer for 4. Okay. So that's why we didn't store our DP with index and we stored our DP by value. Now, whatever would be the answer, I would simply store it in DP of 4. Okay. So let's come back again to segment tree. So what is segment tree? Segment tree is the method which I told. Segment tree is basically a data structure which helps us to do perform range queries. Means if we have to find anything in suppose in certain range, let's say 0 to 4 or 0 to 3, then it helps to find it in log n complexity. Okay, so whatever is the size of array, suppose if you want to find the maximum of maximum from L to R, then it would find that in log of n query. And it also, what is the main benefit of it? It also allows us to update any value, and that also in log n value. Okay, so these are the basic properties of a segment tree. So if you can read about it. So here, how we would create a segment tree? We would create a segment tree on a DP vector, or we can say a DP value on a DP vector. So it would store the value from 1 to till n minus 1. Okay, so initially all the values would be 0, 1. We are not going in depth of how these queries are generally working. Okay, so you can find it on your own. Okay, because it's a whole another lecture on that only. So now if we are performing some query, initially all the values would be 0. Let me write down DP values. Okay, let's say our query was something like this. Okay, so now what we are iterating? First, our let's say there is an answer. We are storing an answer. Initially it is 0. Now let's find out how many subsequence would end here. Okay. So what we want the answer for how many subsequence would end at 2. So one is this answer plus equal to 1 is the value itself, that is 2 itself. What would be another value? Another value would be, let's first store this. Okay, so let's say how many index would end at 2. So one would be the index itself, and what are the others? So others would be ending at 1 and again ending at 2. Okay, so basically all the previous values. So now let's give the query. So what would be the query? We want from 1, comma d of I minus 1. Okay, so we want from index. This is 1, 2. We want from index 1 to 2. Sorry, we want to 1, 0 to 1. Okay, so initially everything is 0. So it would return 0 only. So the current would be 1 only. Now after current, what we would do? We would increase this current in our answer. So we got every subsequence ending at this. Now we would also update our answer for 2 because now we have found how many how many subsequence are there which are ending at 2. Okay, so what we would do? We would perform an update query that would be at 2. So that is v of I, and what would be its changed value? We would increment it by the current value. Okay, this would be our algorithm, and at last we would return answer. So if we perform a dry run, initially this would be 0, everything would be 0. So ending at this would be 1. So it will get changed to 1. Now the index 2 would have 1 as answer. Now next time when we would perform for 3, what query we would perform? We would perform 0 to 2. So it would return 1. So here the answer added would be 2 because there are two subsequence ending at 3, and it will also update the answer here also. So now it will be 2. Now for 5, what it will give us? It will give us the value of this range. So it would be 3 and 3 plus the amount itself. So now it would be 4. Okay. So now it will also update this value as 4. Now for 1, it will give 0 and it will update subsequence ending at 1 by 1. So it will be 1. Now for 4. So 4 would be, it will return 2 plus 1 plus 1. So it will return 4 and the 1 for itself. So here the answer would be 5 and it will also update the answer here. Okay, now for 7, it will return the sum of everything till 6 and 1 for itself. So it will be 4 plus 4, 8 and 8 plus 5. So it will be 13 plus 1, 14. It will also update 14 here and similarly for 8. So at the end, we would get addition of every, we would get the answer for ending at every index. Okay, so that was the algo. Now, if you see in the question, there is one more issue. Okay, so what we did, we can perform the DP. We have created the vector by on basis of value, but here the value can go till 10 to the power 9. Okay, so now it's a issue because now we can't create any array of 10 to the power 9. So now what can we do? Now, if you think about it, then we don't actually require the exact number. Means if we suppose this is the array. Okay, let's take some bigger values. Okay, let's say this is the array in sorted order. Okay, so these are the numbers in the array. So do you guys think that I would require all 100 to 200 steps here? Okay, because there is no number lesser than 200. So what do I really need? I only need the relative order of every index. Okay. So if I sort this and if I number this way, okay, then I got the relative order of every number. Okay. So how many numbers from this I can find out how many numbers are smaller than 300. That there is just one number that is at index 0. That is now represented as 0. Now for 2 I got 1 and 2. If even if I add 400 here, then this would become 2. Then this would become 5. Okay, so this is called coordinate comparison. Okay, so we actually didn't want the exact value. We only want the relative order. So that we can compare. Okay, so we know that all the values lesser than 300 only can come before this. So we don't want the actual values lesser than 200. Okay, if we compare this one with this 0, then also we can get the same result if we compare this. So for that, what we would do, first we would insert every element in our set. Okay, let's create a set. Insert every element in that so that it will give us a sorted order. Okay, so now what I would do, I would map everything in increasing order. And now suppose if this was the initial array. Okay, suppose this was the initial array. Then simply I will replace this with their with their relative value. So it would be 2, 1, 0, 3, and 2. Okay, so it got converted in smaller values. So now now 10 to the power 9 is not an issue for us because now the maximum value which we can create is if all the elements are different, then also we can get it under 2 to the power 10 to the power 5 values. Okay, so now we can create that size of that array and we can solve this question easily. So basically, there were two concepts which are required. First was segment tree, and as I said that we were taking why we were grouping every DP with its value instead of its index, etc. And the second was this coordinate compression. Okay, so for segment tree, you can go through this article. Okay, it's very nice, and for this we only require this, the simplest form of segment tree. For this we only require this first question. Okay, it basically shows. Okay, so this was the first problem. Sum queries. Okay, we want the sum from L to R. Okay, so if you even read this, it explains nicely how this is working. Even if you don't know what you can do, if you want to solve this question, then what you can do, I also have taken this code only in my code. Okay, so you can see my code. I have just copied this whole code here. Okay, so you can also use it as a black box. Although I know how, although I can solve the questions from segmentary, I have used this initial template only so that you guys can refer to this and you can understand. I also have created my own template, but that's different from this. Okay, so what we are doing, this is the code for segmentary. We are taking the input. Now here from this part is coordinate compression. Okay, till here. What we are doing, created a set, insert everything inside the set. Now mapped every element in increasing order from 0. So 0, 1, 2, 3. And now mapping to the original array. Okay. Now what we are doing? Now we are building our segment tree. And here the same algo as I have explained you. Answer. What is the current value? V of I. So we want everything from 0 to current minus 1. Suppose the current value is 2. So we want everything from 0 to 1. Okay. And plus 1 for itself. Modulo M. So we are also adding this to our answer, and we are also putting update on this. Okay, so we are also performing the update. So we are also adding it to the initial DP vector. Okay, so that was it, guys, for today. So after this, we have completely solved every dynamic programming question available on CSES. Okay, so see you in the next video. You guys can comment which next part you want, so I can create on that also. Okay, so please give the feedback on this series, and thank you guys for watching.